Welcome to the deep dive. We cut through the noise, giving you the essence of expertise. Today, we're jumping into a field that really shapes your everyday experience. Think comfort, safety, productivity. We're talking human factors and ergonomics.
Right. It's all about systematically studying how people perform.
Hmm.
The natural laws governing that performance, and then using that knowledge to optimize design, make things safer, more effective.
And the scope is huge, isn't it?
Oh, absolutely massive. It stretches from like the big picture, how a whole company's schedule shifts, maybe right down to the tiniest detail, like a single muscle fiber contracting.
So it's way beyond just, arranging furniture. It's designing the whole human system interaction. And there's a specific starting point for the formal name, right?
There is, yeah. The actual term ergonomics, it was formally put forward in the summer of '49. A group met in Oxford, England,
Okay.
and they combined the Greek words ergos, meaning work, and nomos, meaning natural laws, ergonomics.
Mm.
But the ideas,
Mm.
well, they were definitely around much earlier than that.
For sure. The sources trace it back to the early 20th century. Frederick Taylor, scientific management.
Exactly. Taylor's work. People talk about lots of aspects of his work, but his experiments with shovels in the steel industry, that's pure HFE, really.
Tell us about the shovels.
Well, he watched workers moving stuff, coal or whatever, and he systematically studied it. He figured out, if the shovel's too big, the worker gets tired out too fast over a whole shift.
Makes sense.
But if it's too small, they waste too much motion, too many trips. So he found this sweet spot.
Which was?
Maximum productivity happened when the shovel consistently carried about 21 pounds. Didn't matter what the material was, the load should be around 21 pounds.
So he designed different shovels for different materials, all aiming for that 21-pound load.
Nicely. Engineering the tool to fit the person's capacity.
Yeah.
That's fundamental HFE right there. Simple, but foundational.
And yeah, optimizing a shovel, that boosts efficiency. But if you ignore these kinds of principles, things can get serious fast. It brings us straight into the legal territory, doesn't it? Product liability.
It really does. The message there is pretty stark, actually. If there's a design defect, something that causes an accident or a health issue,
Mm-hmm.
and if that defect could have reasonably been foreseen and fixed beforehand, well, the company's responsible. It's not just a nice-to-have anymore. It's a legal must-have.
The source material points to a tragic but really clear example, the fuel tank design on the Ford Pinto.
Yes, that's the classic case study, unfortunately.
It just hammers home that thinking about human factors isn't optional. It's not just about making things smoother. It's fundamental to safety, and there are real legal consequences.
And what's interesting is how the process works. It doesn't start with building a thing. It starts much earlier with defining the problem itself, which leads us neatly into human-centered design, HCD.
Okay, HCD, let's unpack that a bit for the listener. Say you're designing anything, really a tool, software, a whole workflow. Where do you absolutely have to begin?
You start with principle 1 to 4, which basically says you must be sure the problem you've identified is the right problem, and, just as important, that you've formulated it correctly.
Okay. Why is that so critical?
Because it's incredibly easy, frighteningly easy actually, to pour millions of dollars and tons of effort into creating the perfect, elegant solution to the wrong problem. Or maybe a problem that isn't the main issue.
Right. The old trap of building a faster horse when you should be inventing the car.
Exactly that. And then when you're looking at changing an existing system, there's another layer. Principle 1 to 8 comes into play. This is more about the social side of design.
What does it say?
It advises that, as much as possible, you should only change the parts of the system that the actual users, the personnel already working in it, feel need changing.
So don't just change things because you think they're inefficient, even if the operators like them.
Well, you have to be very careful. If you, as a designer, come in and take away features or change workflows that people rely on, even if those ways seem clunky to an outsider, you risk losing their trust.
They see you as an adversary.
Sometimes, yeah. They feel like they're losing control over their own work. And what happens then? They often find ways, sometimes quite creative, sometimes, frankly, counterproductive, to work around your supposedly optimized new system. Getting buy-in from the users is just as vital as the technical fix itself.
That's a really key point. Design isn't just engineering, it's psychology too. Okay, so let's shift focus now to the actual human machine we're designing for the body.
Right, the physical side.
Yeah.
We often model the musculoskeletal system using mechanics. Think of it as a system of levers.
Levers, how so?
Your bones are the rigid links, the levers themselves. Your joints act as the fulcrums, the pivot points,
Uh-huh.
and your muscles. They provide the force, usually by pulling, creating tension. Ligaments often provide opposing tension.
Okay.
Take your forearm, for example. When you lift something or even just hold your arm out, your triceps muscle might be working to stabilize or extend the elbow. But the point where the muscle attaches to the bone is often very close to the joint, the fulcrum.
So it has a short lever arm.
Exactly. Yeah. Compared to the lever arm of the load you're holding out in your hand, or even just the weight of your forearm itself.
Which means if I'm holding something relatively light, say a book, my muscle has to pull much harder than the weight of the book.
Disproportionately harder, yes.
Yeah.
Because of that mechanical disadvantage, that short lever arm for the muscle, the internal forces generated by the muscles can be dramatically higher than the external load you're actually dealing with.
Wow. Okay.
And that huge internal force gets transmitted through the system. It results in really large compressive forces acting on the bones and especially within the joints. This is why things like posture and repetitive strain become so critical.
And that brings us to some common problems, right? The cumulative effect of these forces.
Absolutely. Carpal tunnel syndrome, CTS, is a prime example. It's a cumulative trauma disorder, very
And
common.
what's happening there?
Essentially, swelling and irritation builds up inside the carpal tunnel in your wrist, putting pressure on the median nerve. And it's strongly linked to tasks involving repetitive grasping, especially with significant force, combined with awkward wrist postures, like bending.
Okay. And what about back pain? That seems almost universal.
Low back pain, yes. The bane of many workplaces. It often stems from, well, moderately poor posture held for long durations, sitting hunched over a desk all day, for example.
Or lifting incorrectly.
Or lifting heavy loads, especially with poor posture, bending and twisting at the same time is particularly bad. The compression forces on the lumbar vertebrae can be immense, really damaging over time.
Okay, so that's force and structure. What about energy? How do we measure human capacity for work over time, stamina?
That gets into metabolic rates. It's all about oxygen consumption, fundamentally. Muscles need oxygen to work, to contract.
Right.
If you suddenly start doing something intense, like sprinting, your muscles use up the oxygen available locally faster than your circulatory system can replenish it. That creates an oxygen debt.
Is that when you feel the burn? Lactic acid.
That's exactly it. Lactic acid builds up as a byproduct when you're working anaerobically without enough oxygen. We quantify the energy cost of different activities using a unit called METs.
METs. Metabolic equivalents. Give us a feel for those numbers.
Sure, it's a ratio, really.
Yeah.
Just standing quietly, that's your baseline. 1.0 MET. Driving a car takes a bit more energy, maybe 1.5 METs.
Okay.
Riding a horse at a walk, that's about 1.6 METs. But something really strenuous and sustained, like playing American football, that can be up around 7.9 METs.
Wow, big difference.
Huge. And knowing these metabolic costs allows designers or planners to figure out reasonable workloads, how long someone can sustain an activity, and when they'll need rest breaks to recover.
Okay, fascinating. So we've looked inside the body. Now let's look at the environment around the body. How do we measure and design for things like heat, light, noise to keep people comfortable and performing well, whether they're the 1.0 MET typist or the 7.9 MET athlete?
Right, the external factors. For temperature and thermal comfort, it's about heat balance. We use a basic heat transfer equation. You track the heat the body produces, that's metabolic heat, the M, and then all the ways heat is exchanged with the environment.
Like conduction, convection.
Conduction, convection, radiation, and crucially, evaporation sweating. That's C, C, CV, R, and E in the equation. The goal is for heat production and heat loss to balance out, keeping the core body temperature stable. That's S for storage, ideally 0.
And there's a specific unit for clothing insulation.
Yes, the CLO unit.
Okay, what's a CLO in practical terms? Give us a non-lab coat example.
Okay, think about it like this. 1 CLO is roughly the insulation you get from a typical business suit. It's defined as the amount of clothing needed to keep someone sitting quietly comfortable in a standard room around 70 degrees Fahrenheit, normal humidity, slight air movement.
So knowing the CLO value helps design.
Everything from office wear standards to high-performance gear. How thick does that sleeping bag need to be for a specific temperature rating? How many layers does an astronaut need for a spacewalk? It's about quantifying thermal resistance so you can design effectively for different environments.
Got it. Moving on to light. We intuitively know like it's dimmer further away, but how quickly does it drop off? Is it significant for design?
Oh, it's very significant. The physics tells us that illumination on a surface falls off with the square of the distance from the source.
The square. So double the distance means.
1/4 of the light intensity. Triple the distance, only 1/9 the light. It has huge implications for laying out workspaces, ensuring adequate lighting on task areas, safety lighting on factory floors, things like that.
Mm.
You can't just put a lamp anywhere.
And how our eyes use that light. It's not just about brightness, is it? There's more complexity.
Definitely. A key distinction is between static visual acuity and dynamic visual acuity, or DVA.
Okay, what's the difference?
Static acuity is what they test with a standard eye chart reading stationary letters on a wall. DVA is your ability to see and identify targets that are moving.
Ah, okay.
And here's the kicker. The sources emphasize there's almost no correlation between the two. Someone can have perfect 20/20 static vision, but be terrible at tracking moving objects, and vice versa.
So you can't assume good eyesight means good DVA. Why does that matter?
Think about designing controls or displays for anything that moves a car dashboard, aircraft instruments,
Right.
even monitoring items on a fast-moving conveyor belt. You need to design for DVA, not just assume static acuity is enough.
Right, critical distinction. Okay. Final environmental factor. Noise. We know loud noise is bad, causes hearing damage, temporary threshold shift, eventually permanent loss. But how do we control it in design?
Well, there are many strategies: absorption, damping, isolation. But one of the simplest and most effective is Principle 413, increase the distance.
Just move people further away.
Pretty much. Similar to light, sound intensity also decreases significantly with distance, roughly with the square of the distance in open space. So doubling the distance between a noisy machine and the worker can cut the sound energy reaching them by about 75%.
So distance is often the cheapest form of noise control.
Often, yes. It's a really powerful fundamental tool in the noise control toolkit.
Okay, this is great. We've covered the body, the environment. Now let's zoom way in to the micro level. Analyzing individual motions. This brings us to the Gilbreths, right? Frank
Yeah.
and Lillian Gilbreth.
Yes, the pioneers of motion study. They wanted to break down every single task, every movement a worker made into its absolute smallest components.
And they came up with a special name for these components.
They did. Thurbligs.
Thurbligs. It sounds like something from, I don't know, a Dr. Seuss book. Wait a minute. Gilbreth. Thurblig. It's almost backwards.
It is Gilbert spelled almost backwards. Yes, that's exactly where it comes from. One of those quirky bits of scientific history.
So they named fundamental units of motion after themselves, backwards. That's amazing.
It is pretty memorable, but
Yeah.
the point was serious. To identify every tiny motion reach, grasp, move, position, release, and so on, and then figure out which ones were actually productive versus which were non-productive, essentially wasteful.
Okay, so what counts as a non-productive Thurblig? What are we trying to get rid of?
Good examples are hold, where you're just using your hand as a passive clamp, a fixture,
Yeah.
instead of actively working. That's usually inefficient. Or preposition.
Preposition.
Yeah, that's when you have to orient an object, get it ready before you can actually place it or assemble it. If you can design the workspace or the parts themselves, so prepositioning isn't needed or is minimized, you save time and effort.
So the design principle is eliminate or drastically reduce those non-productive Thurbligs.
Exactly. Fewer wasted motions mean faster task completion, usually better accuracy, and often safer work because there's less unnecessary handling or awkward positioning.
And this incredibly detailed focus on time and motion eventually led to models that could predict how long movements should take based on difficulty.
Right. That leads us to Fitts' law. It's a really elegant model that predicts the time required to move to a target area as a function of the distance to the target and the size of the target.
So speed versus accuracy.
Precisely. If you need to move quickly to a large target, it's fast. If you need to move precisely to a very small target, like threading a needle or clicking a tiny icon on a screen, Fitts' law predicts it will take more time. It quantifies that speed-accuracy trade-off. It's incredibly relevant for designing interfaces, assembly tasks, anything involving aimed movements.
And industries use this kind of microanalysis to set standards, don't they? Even without watching every worker?
They do. There are systems called predetermined motion time systems, or PMTS. Things like MTM methods, time measurement, or work factor.
How do they work?
They're built on huge databases of times for basic motions, the Thurbligs, essentially. You break down a planned task into these elements, look up the standard times, add them up, and you get a predicted time for how long the task should take.
Without needing someone to actually perform it first?
Correct. It's often based on the performance of a mythical standard operator, someone working at a defined, consistent, normal pace. It allows for planning, costing, line balancing, all before production even starts.
Wow. We've covered a massive amount of ground. From that 1949 meeting in Oxford and Taylor's 21-pound shovel, all the way down to predicting movement times in milliseconds using Thurb legs and Fitt's law. This field really is about meticulously fitting the designed world to the humans in it.
It truly is. And that focus sometimes pushes into really interesting, almost philosophical areas. Take fuzzy set theory, for instance.
Fuzzy sets, that sounds imprecise.
Well, yes and no. It's actually a mathematically precise way to handle imprecision specifically, the kind of imprecision inherent in human language and judgment.
Oh, so?
People naturally use fuzzy terms. We describe someone as young or tall, or say traffic is heavy, or a room is warm. These aren't exact binary categories. They have degrees of membership. Fuzzy set theory provides tools to model that vagueness mathematically.
So you can quantify subjectivity in a way. How would
Yeah.
you use that in design?
Think about control systems. Instead of rigid thresholds like, if temperature is exactly above 75, turn on fan, you could use fuzzy logic. If temperature is quite warm, turn fan on low. If very hot, turn fan on high. It allows for smoother, more human-like control based on these less precise but very natural descriptions.
Interesting. It bridges the gap between rigid machines and flexible human perception. Okay, let's wrap up. We always like to leave our listeners with a final thought to chew on.
Right. Well, here's something that comes out of consistently applying ergonomic principles, kind of a dual benefit. When designers make the effort to design for the extraordinary person accommodating people with disabilities, or those with very different physical or cognitive abilities,
Okay.
that process almost always teaches them valuable lessons about how to better design for the so-called ordinary person as well. Thinking about the edges cases, the extremes, often reveals insights that lead to more intuitive, more forgiving, just better designs for absolutely everyone. Universal design benefits all.